Alright, in this video we're going to take a look at coding our DirectSound SoundEngine.
Which in itself is not going to be particularly difficult, but there is a lot more to it than what we did with the Exact engine.
Right, there's simply the fact that we have to get our hands dirty with some of the audio data that is going to be passed on to DirectSound.
Right, we've got to manage some of that ourselves. Alright, let's go ahead and get started.
Alright, let's go over here to our project. I'll collapse up the content subproject just to give ourselves some more room here. Then we'll right-click on SoundEngine and add a new class. We'll call this class SoundEngine Direct Sound. And we'll hit Add. We'll make sure that our new SoundEngine class extends the base SoundEngine. Now, before we drop some using statements in place, since we are indeed going to need to reach out and grab DirectSound, we'll need to include SlimDX here as a reference, because of course we're going to be using SlimDX to access DirectSound.
So we need to reference that library.
So we'll jump up here to References, we'll add a reference, and we'll give it a minute to populate this list. Then under .NET, we need to scroll down to S. I'll just hit the S key on the keyboard to jump down here, and the first option we have listed is SlimDX. We'll hit OK to get that added in. We can see it added in into the list of references. And now we'll go ahead and throw some using statements. We are going to need the standard Microsoft XNA framework, so we'll drop in using Microsoft.xna.framework. And we need to open up a couple of the namespaces inside of SlimDX. So we'll put down a using for SlimDX.DirectSound.
Makes sense.
And we're also going to open up the SlimDX. Let me get some of this typed out. SlimDX.multimedia. This namespace contains a helper class, a type of stream that is going to aid us in loading and interpreting wave data.
Okay.
Alright, now we can turn our attention to the class itself. We need a couple of fields set up, and those fields are going to be a reference to a DirectSound device, and we are also going to keep a list of sound buffers so that we can access these buffers by index and facilitate the implementation of the play method.
Right, and these sound buffers are going to be analogous to just the sounds that we were playing in our last engine.
Yes, very similar, whereas in the XNA engine, all we had to do was remember the names of sounds,
Sure.
and XNA would handle the rest of it for us. Here we actually have to hold references to real actual data containing buffers that we can then address through DirectSound to cause sound playback.
And those buffers will contain some information on how to play the sound as well as the actual data for the sound itself.
Exactly. So let's get these fields dropped in. The device is going to be of type DirectSound, so we'll call this field device. And we will make a list to contain our sound buffers. So we will make a list of type sound buffer, and we will call this list sound buffers, and we will create the list using a field initializer. So new list of type sound buffer, and there we go. Alright, now we're ready to move into some methods. We'll begin with the initialize method.
Okay.
We'll override the SoundEngine.initialize method. We will wipe out our call to base,
Which is empty anyway.
and we will begin by creating a new DirectSound device. So we will say device is equal to DirectSound, or excuse me, new DirectSound.
New DirectSound, right.
Since we're instantiating a new instance of this class. And then we'll turn around and we need to give this device, this DirectSound device, some information about ourselves as a program. Basically, DirectSound needs to know about our game window so that it can be aware of when the window gets minimized to possibly mute sounds and keep an idea of whether or not the window is still in existence.
Okay. Now this is functionality that is particular to DirectSound, yeah?
Yes, this is correct. This is just something that DirectSound wants to be able to, well, for lack of a better word, cooperate better with our game. And that's exactly what we're going to be gaining access to right here. If we take our device, we have a method called setCooperativeLevel. Cooperative level is going to need to take in a pointer to our window handle, and it's going to need, or rather it's asking for what level of cooperation does it want, meaning how much attention is it going to give us.
Okay.
Now, for the window handle, we can look into the current game instance, which contains a window property, and that in turn contains a window handle. So we'll look at this parameter that's being passed in via game. We'll say game.window.handle.
Easy enough.
And then for the cooperative level, if we look at slimdx.directsound.cooperative level, we find that we have normal, priority, and right primary. We're just going to go with priority to give ourselves high priority as opposed to just normal play along with everyone else. The idea is here, since we're making a real-time game, we do want priority access to direct sound.
Right.
All right, moving on. Now we need to address the load sound method.
Now this is where a lot of the real work takes place, because rather than having some assets that we already created in an external tool such as Exact, and having an engine that will just deal with those assets kind of behind the scenes, we have to go in and manipulate some data and establish some buffers that not only tell our engine what data is going to be played, but how it's going to be played back to us.
Exactly. So we're going to need to do a little bit more work here where we need to get an actual file. We need to look at the data in that file, utilize some of the types available in SlimDX to read the file, and then do some work with buffers in memory to finally get the data over and ready and usable by DirectSound.
Right.
So, beginning off, we need to override the load sound method. Once again, we do not need a call to base, and we will begin with a temporary data container. In the process of getting information from a file, then to memory, then over to DirectSound, we're going to need to make a temporary container in memory to hold data while we get a buffer ready to contain that data.
Okay, it sounds more complicated than it really is. Later on, we're going to be reading and writing some data, and in effect, our system's going to be looking for data to be pulled out of a byte array.
Exactly, and we need a container to exist so that in one operation we can get some data, and then later down the road we can look back at that data and put it somewhere else.
Yeah.
So we'll make this byte array. We'll define it as, let's see, byte array data buffer. Now let me change the casing on that. We'll do like so. And of course we're defining this here as a local variable. We won't worry about actually creating the array until we know how big the array should be. And we won't know how big the array should be until we know how big the incoming WAV file is.
Okay.
So, moving on from here, we're going to create a new wave stream. Wave stream is a class provided by SlimDX. It allows you to use stream-style functionality specifically on WAV files.
Okay.
It's very handy because it will go into the WAV file and actually separate what part is the header or properties of the WAV file opposed to the raw data of the WAV file. So it'll separate these two things for us and make them easier to read.
And what we're interested in right now is just that raw data.
Exactly, because we need to get that loaded into data buffer. So we'll make a new wave stream variable. We'll simply call this wave stream. And we will instantiate a new wave stream, and WaveStream's constructor takes in a path. So we need to immediately feed WaveStream the incoming file. And we're simply going to plug sound name in here. So we're going to imply that anyone using this DirectSound SoundEngine is going to feed us WAV files via the sound name.
Gotcha.
All right, as soon as we get this WAV file loaded up, we will know how big it is, because at that point we can read the wave stream's properties and figure out how much data we're dealing with. So at this point we're going to go ahead and create our data buffer. So we'll say data buffer is equal to new.
Now we can plug some data into it.
Exactly, new byte array, and we know how big to make the array. So for the size of the array, we'll drop in wavestream.length.
So cool, we're making a data buffer, which is actually a byte array of the size of however long our wave stream happens to be.
Exactly, and that ensures that the data buffer has sufficient space to store all of the data in WaveStream.
But we haven't yet written that data into the data buffer.
That's correct. All we're dealing with here is a nice created, allocated, but otherwise empty array.
Right.
So we have all of our bytes ready to store information, and at this point they should all be zeroed out because we haven't written anything yet. So now we're going to do just that. In the next operation, we're going to get the data out of the wave stream and put it into the data buffer. And we're going to use this by using the read method on the wave stream. So we can tell our wave stream to read some data, basically read data out of this wave file. And when we do the read operation, we're going to need a few things. One, we need to tell the wave stream where it should put the data.
This is actually important. Before you type anything else, you can see right there in the tooltip that this method is actually looking for a byte array.
That's correct. We've got down here byte array buffer. So that, again, ties back to our temporary data container.
Right. It kind of brings everything full circle as to why we chose a byte array to store the information from WaveStream.
So let's go ahead and start filling some of this out. We'll drop in our data buffer as the byte array. Then we need two more pieces of information. First is an offset, and second is a count. What this does is the stream reading functionality gives us the ability to load part of a file. We're not forced to load the entire file at once. We can actually load individual pieces of a file. Now in this case, our samples are relatively small, and we want to load entire wave samples into entire sound buffers, so we're going to read the whole file at once.
Right, because the whole nature of the wave stream is that it's already pulled out any header information, stuff that we don't need, and all we have right now is the raw data from the sound itself.
Exactly.
So we want all of that.
So we're going to grab everything. That means our offset will be 0 to indicate that we'd like to start reading at the very beginning of the file, and count is going to allow us to specify how many bytes should be read. In our case, we want all of them, so we'll specify the length of the wave stream. So we'll plug in here wave stream dot length.
This is going to lead to a little bit of an issue.
It is. You'll notice if we pause here for a moment, the interpreter, or rather IntelliSense, comes up and tells us that we have an invalid argument here. Basically, read was requiring an integer for the count, and length is in a long. So we have a 64-bit number indicating length. Here in this case, though, we're not going to worry about overflowing even a standard int, because we're not going to worry about something like 2 gigabyte wave samples.
Sure.
We know that since these are individual instrument samples, they're all going to be relatively short. So that means we can safely cast to integer, discard the extra 32 bits, and simply use length casted directly.
Cool.
All right. Now we have, at this point, loaded the data from our WAV file into data buffer. So now it's time to address the sound buffer, an actual DirectSound sound buffer.
And what this is going to do is essentially reconstruct the header information. It's the same type of information that you'd usually find in a WAV file's header.
That's right. Before we can jump into the sound buffer itself, whenever you create a sound buffer, you will have to describe to DirectX the properties of this buffer. And by properties, I mean what is the sample rate going to be? Is it going to be 22 kilohertz, 44 kilohertz, or so on? What is the number of channels? Are we dealing with mono or stereo? A lot of audio-style properties.
We can also look at this in another way, that our sound buffer needs to really contain two key pieces of information. One is the audio data itself, and the other is how you're going to play that data.
Exactly.
And so what we're going to do now that we've got the raw audio data set aside in our data buffer, we're going to create the description of how that audio data should be played back.
Exactly. In order to do this, we're going to create a sound buffer description. So we'll make a local variable of type sound buffer description, and we'll abbreviate the variable name. We'll simply make something called SDESC for S description, and we'll create a new instance of sound buffer description and store it in that variable. Now, we're going to set up a few of the properties of our new sound buffer description. We'll begin with sDescription.format. Now, format is actually of type wave format, and a wave format itself really contains a lot of the header style information that one needs in order to play audio. Now, instead of delving into the format's individual fields, we can leverage the fact that the wave stream actually loads up all of the properties of the wave file into a wave format object. And that object can be accessed by WaveStream. So we'll say equals WaveStream dot, and if we type in format, you see that is of type wave format, and we can simply patch that directly in.
Right, so basically the wave stream has already grabbed the important information it needs from the wave file's header, and now we're going to be adding that into our sound buffer description. in effect, we're just taking this data and putting it into our system in a way that our program can understand.
Exactly. So, moving on from here, we need to set up a few more properties of the sound buffer description. The next step is the size in bytes. So, exactly how much information are we dealing with the sound data? And we'll simply use, once again, the wave stream to read out the length of the data. So we'll look at wavestream.length. Now, once again, you'll notice a type difference here where length is of type long and some size in bytes is looking for an integer. So we'll simply cast this over to int.
Now, just as a random point of trivia, could you not also, if you wanted to, use the length of the data buffer?
We could. Since the length of the data buffer is based on the wavestream length, we could simply use databuffer.length here instead. But in this case, since we're referencing wavestream for so many other things, we'll just go ahead and use it for...
Yeah, I was just throwing that out there as one of those random points of trivia.
But yes, you could use anything that held the length of your data, including an arbitrary integer that was returned when you read the data out to begin with. So anything that accurately describes how many bytes of information you're working with is applicable here. All right, one last thing we need to do when addressing our sound buffer description is to set a specific flag. So we're going to look at sDescription.flags, and we'll set this equal to bufferflags.stickyFocus.
What are you doing this for? Because this looks like one of those things that you wouldn't know about unless you were already familiar with DirectSound and SlimDX anyway.
Right, what this is going to do is indicate to DirectSound that it should not mute the sound in the event that our window loses focus.
Okay.
By default, DirectSound will try to keep an eye on the state of your window, and the moment it goes behind another window or otherwise goes out of focus, it will mute the sound for your app, generally to make it play nicely with other apps or games, so that the game in focus is the only one making sound.
And a lot of games do this.
Now, in our case, especially for some of the later modes in the game, it can actually be useful to have the game continue to play sound even if you switch over to another app or lose focus.
Mm-hmm.
So we're going to go ahead and enable sticky focus to tell or to indicate to DirectSound that it should just keep playing sound as long as we request sound to be played.
But if later on when you were wrapping up an official game that was using a system like this, you could pull this out if you wanted your sound to go away when you drop focus.
Exactly. If you package this game as an end-user product that was meant to be played in a normal fashion, possibly along with other games, then you might want to re-enable the default behavior. But now that we have created a sound buffer description, we now have all of the necessary information to create the sound buffer itself.
Right, well, we have our two key components. We have the raw audio data itself, we have the description, which basically tells how we're going to play back that data, and we're ready to combine those two together and put them into a final sound buffer.
All right, let's create the sound buffer itself. We'll make a variable of type secondary sound buffer. And we'll call this sound buffer. And we will create a new instance of secondary sound buffer. Now, when we create our sound buffer, that sound buffer is going to need to know what device it is associated with, and it's going to need a description, a sound buffer description. Mm-hmm. Now, of course, the device is the device we created earlier to work with DirectSound. So we'll simply specify device and sDescription, and that should satisfy the constructor of secondary sound buffer and create a brand new sound buffer for us to use.
Now, without trying to get too heavily into DirectSound, and I know you're probably going to cringe a little bit when I ask, but why are you actually calling this secondary sound buffer? Or why are you drawing on secondary sound buffer?
Well, this is all based on the architecture of DirectSound itself. Mm-hmm. Basically, DirectSound has a primary sound buffer, it has a single primary sound buffer, and then it may have any number of secondary sound buffers.
Right.
The idea is every secondary sound buffer contains exactly one sample. Mm-hmm. And DirectSound also contains a set of mixing engines, and it is able to mix the secondary sound buffers on demand into the primary, where the primary is then fed on to the sound card.
So in a nutshell, we don't really want to mess with the primary buffer, because that's going to be mixed together by DirectSound on its own.
Exactly. We wouldn't mess with the primary sound buffer unless we were in a situation where we wanted to write an audio mixing engine ourselves.
Right.
If we wanted to take some arbitrary buffers and mix them together, then we may want more direct access.
Right. We're just basically putting some sound effects on an assembly line so that they'll get piped into direct sound, combined together, and then output later on. To do that, we've got to go to the lowest, kind of the background level, which is the secondary sound buffer, so that later on those can get piped onto the primary.
Exactly. Another way to look at it is we're simply leveraging the fact that direct sound can mix an arbitrary number of secondary sound buffers.
Right.
So if we make a bunch of secondary sound buffers and then invoke some playback on those buffers, direct sound will handle everything from then on out.
Good enough.
Alrighty. Now that we have a new sound buffer, we want to write all of the audio information into that buffer.
Right.
Because at this point, direct sound doesn't really care that we have a WAV file up here. It doesn't work directly on WAV files.
Right. Well, currently our buffer has just been created, and it's been associated with our device and with our description, but currently there's no data in it.
And beyond that, the sound buffer doesn't even care that we have data in memory in our data buffer.
Sure.
It wants its own buffer, or rather it wants to be managed by direct sound in such a way that direct sound itself has more control over it.
Right.
That means we're actually going to need to copy the data out of our temporary buffer and write that directly to the sound buffer itself.
And again, this is where we're going to come up with kind of a confirmation as to why we needed that byte array in the first place. Because in order to write this data into the sound buffer, it's going to tell us we need a byte array anyway.
That's exactly. Once we invoke write, write is going to be looking for a byte array. So let's put this together. Let's take sound buffer and invoke the write method. And write is going to be looking for a typed array, in this case a byte array. So we will drop in our data buffer. Then we need to indicate an offset into that buffer, and since we're looking for the entire buffer, we'll set our offset to 0, so indicate that we want to begin at the beginning of the buffer. Now this last thing is a little bit interesting, though we don't really have to look too deep into it. We have this thing called lock flags. And the idea here is that we need to lock a sound buffer or part of a sound buffer before we write to it. And this gets into some more advanced topics, such as streaming continuous data to a single buffer.
Right.
Now in this case, we're not actually worried about streaming. We're just looking to, one time and one time only, load data into the buffer and be done with the write operation.
So it's kind of like saying grab all of the information from that buffer and then close the door behind you.
Exactly. So we're going to use lockflags.entire buffer. Since we're not worried about a situation where part of the buffer is being used for playback and the other part is open for writing, since we're setting up the buffer from the beginning, we need to fill the entire buffer. We'll just block the entire buffer and write all of the data to it in one run.
Cool.
All right. After this operation completes, we now have all of the data loaded directly into the sound buffer itself. So at that point, we're done with the sound buffer creation. Though we do need to remember not only that we created the sound buffer, but we need to drop it into an indexed system, or in our case a list, so that we can get back to it later for playback.
Which we've already created. We created a list early on called sound buffers.
So if we look at that list, we have our sound buffers list. We can add an item to that list, and we'll simply add the newly created sound buffer. And once we have that sound buffer packaged away into our list, one last thing we'll do is we'll make sure that at this point we let go of that WAV file. Since in order to open up and read the WAV file, we of course have to gain a handle to it, and that means our application is going to hold that file open.
Right.
In order to let go of that file, since we're done with it, we'll simply run wavestream.dispose to allow it to clean up any internal data and especially any file handles that may have been created when creating the wave stream itself.
Okay.
So with that, that has our load sound method taken care of.
Very cool. And yeah, obviously a little more involved than the one we did for the XNA engine. But once you get the idea of what we've got to do here, we've got to grab that data right out of the WAV file, put it into a temporary byte array so that we can read and write, basically. Really, we're giving ourselves the ability to read data from it, etc. And then we create a description, which is in effect the same thing as a header. Combine the description as well as our data back together into a sound buffer. It's really not that bad.
Exactly. Just getting everything over to a format that direct sound will work with.
Right.
All right, moving on from here, we have just a handful of things to tie up, and we'll have our direct sound class finished. The first of those is to provide an override to unload.
So this is something we didn't do with the XNA sound version.
That's right. In the XNA version, we simply relied on the underlying classes to handle any kind of cleanup. Here with DirectSound, we want to make sure that we explicitly release any buffers that might exist and release the device itself. Tell DirectSound that, okay, we're done using the sound card, you can have it back, other programs can use it, or whatever resources may be tied up in using it.
So this would be something that you would call on when the program was closing down?
Exactly. In our case, since the drum game can only use one device at any given time, then in our case, the only time we would ever do this is when we are done playing the game altogether.
Okay.
So, the first thing we need to do, actually there's two things we need to accomplish inside of unload. The first is we need to dispose of any sound buffers we might have created. The second is we need to dispose of the DirectSound device itself. Now to get to all of the buffers, we'll run a simple for each loop. And we'll run this loop over the sound buffers list. So we'll say load each sound buffer into a local variable called sound buffer. So for var sound buffer in sound buffers, we will simply take each individual sound buffer and we will call its dispose method.
So you're just trashing each thing you find?
Exactly, just telling it if it was using memory, clean that up. If there's any handles internally because of, I don't know, DirectSound internals, those would get released. Also, I'm going to pull out the braces.
Right, because it's only one command.
Because we're only going to run a single line underneath this for each. Now, once we have all of our sound buffers taken care of, we can then turn to the device and tell it to dispose as well. Clean up any handles that may exist linking us to a sound card or any of the other linkage systems inside of DirectSound. Alright, that takes care of unload, and now we are down to our final method for the DirectSound SoundEngine, and that is the play method. So we will override play, and just like we did in the XNA SoundEngine, we will do a check to make sure that the incoming index is within range for our sound buffers list. Then we will proceed to sound buffer playback.
Basically, that we're not trying to play some value that doesn't really exist in our list.
Exactly. So we'll say that if the index is out of range by being less than 0, or if the index is out of range by being greater than or equal to the sound buffers count, then we will immediately return and therefore skip any other code that might be inside of play. All right. Once we have verified that we have a valid index, we'll turn around and turn our attention to the sound buffer. Now there's actually a few things that we're going to do here. We can come back and mess around with these individually, but we're going to drop them all in place from the get-go just to get everything up to par with our other sound engines.
So what you're saying is all of the functionality we're about to add may be the kind of thing you discover after you play with it and do some debugging?
Exactly. We're going to
kind of spare you that.
Exactly. We're going to do several steps all at once, and then once we get everything working, we can analyze these steps more closely to see exactly what they're doing and why they need to be placed here.
Well, how about we just do it like this? Let's just start with what most folks would think you needed to do, which is just play something.
Exactly. If we were just going to look at the sound buffers and play, well, the first thing we need to do is, of course, get an individual sound buffer out of that list. So we could say sound buffers addressed by index.
Right, which we sent into the method in the first place.
So that will give us access to a specific sound buffer where we can call play.
Okay.
Now, play is actually going to take in a few things, though we're not really worried about how these work. We're given the option to set priority and play flags. In our case, everything is going to be set on an even playing field, so to speak, meaning we're not going to assign any higher priority to any individual sound. Everything is going to be set the same.
Sure.
So we'll simply set a priority of 0 across the board. And then the play flags will give us some options to indicate to DirectSound exactly how and with what the sound should be played, if we so desire. Now, if we're not worried about the specifics of what and how, we can set a play flags of none, and that will simply allow DirectSound to decide whatever would be best for this case.
So it's kind of like saying, I don't have any special commands for you to do, just play the sound.
Exactly, just play the sound with whatever method seems most convenient at the time.
Now, if you were to stop here, without actually firing up the program, what kind of problems could you potentially run into?
Well, we would be able to play sound. The problem we would run into is the fact that we would not be able to re-trigger a sound until a sound ended.
So if you had like a 3-second cymbal crash that just kind of dragged out, you and you hit another cymbal crash or maybe even another drum beat, how would that work?
Well, you would have to wait until the entire crash finished.
Gotcha.
Because what's going to happen is play is just going to indicate that playback should start. If this sound buffer is already playing and already halfway through a sample, and we call play again, it's simply going to keep playing.
Gotcha.
That command will essentially have no effect, because we'll tell it to play, it'll say we're already playing, and it will continue to play. That means instead of re-triggering a new crash hit, we're going to do nothing. We're going to let the current crash hit just finish out.
Okay, so how do we fix that?
Well, we're going to interrupt playback, rewind the sound buffer, and begin playback from the beginning.
All right.
Basically force the sound buffer to reset and replay.
So the next thing we'd do would be to stop current playback.
That's right. The first thing we're going to have to do is say, all right, take our current sound buffer addressed by index and tell that sound buffer specifically to stop playing.
And I say the next thing, though. Technically, you'd want to do this first.
Right. You want to get the sound buffer stopped and then play it. Now, one other thing is the fact that stop will not necessarily change the seek or the position of the buffer.
It's kind of like pause on Winamp.
Exactly.
Just ceases playback.
This is much more analogous to a pause style of functionality. So once we have our buffer stopped, in order to accomplish a replay, we need to do one last thing, and that is to seek back to the beginning of the buffer. So we'll do this by saying sound buffers by index dot current play position is equal to 0.
Now, granted, I mean, if you were totally new to this and you were building this on your own, you may have just put in play, and then you would have had to fire up the program and find that, hey, wait a minute, I can't do a whole bunch of cymbal crashes one after the other, and then you would have had to add these lines in. So what we've done is just kind of spared you that and shown you why each one of these commands is in place.
Exactly, just remembering the fact that play simply means to continue playback. So in order to establish a scenario that could be considered a replay method...
You literally have to hit stop and then rewind, and then you can hit play again.
Exactly, we're doing just that here. So with all of these in place, really, that wraps up the SoundEngine DirectSound class.
Woohoo.
Before we move away, we'll do a quick build of the solution to make sure that we have no syntax errors. Everything has succeeded. So let's turn
I don't
our
know how you do it. No matter what I'm coding, if I'm coding 2 lines of anything, I always have at least one syntax error in there.
The answer is IntelliSense. It's the fact that it's very quick to tell you immediately when you mess something up.
Yeah.
All right. Now the next thing we want to do is put our brand new DirectSound into use in the game. So let's switch over here to the game class, and let's get a few things set up. Now before we can jump in and start loading wave files into our SoundEngine, we need to establish exactly where these wave files are coming from. We need to assemble a path that will contain our wave files. So what I'm going to do is jump down here below the SoundEngine field back in our game and create a samples path, a string value, so that we can remember exactly where samples reside. So we'll create a string field. We'll call it samples path, and we'll initialize it with the value of simply samples.
So if you change the folder for this, you'd want to pop in here and at least change that value.
Exactly. This name has to correlate really to the name found over here in content samples, since it's actually this content project that's getting represented or created inside of our game's output directory.
Right,
so,
but currently the problem is that's not a path yet. That's just a word, really.
Exactly, that's just this name. Using a few path combining operations will assemble the full absolute path. And noting that the fact that we're going to be using path combining means we're going to need access to the path object, or rather the path class. So we're going to drop in an additional using statement inside of our game, which is using system.io. Now, to fully assemble this path, let's jump in here to our game's constructor right after we've established the fact that our content project's root directory is named content, as in this guy here. What we need to do is to assemble an absolute path. Now, we need to first gain where the root path to our game itself. Right now, if we switch over to the project folder, we can see that all the way up under here, under debug, the output folder for our game, we can see that there is this big long path starting in C, documents and settings, so on and so forth. Now, fortunately, there is a setting accessible to us via the storage container object. We basically have storage container.titleLocation. What title location is going to contain is wherever our game currently resides. So in that case, that would be equal to this path right here, ending in x86/debug. Now, we need to go a few paths further than this. We need to go beyond this, being the title location, into the content folder, and then into the samples folder. Having done that, we'll have path information pointing at these WAV files.
Easy enough.
So let's do that in code over here with the path.combine method. The first thing we'll do is we'll make a local variable here called content path. And the idea here is that we're going to expand this relative path called content into an absolute path starting at our root directory. So we're going to say that content path is equal to path.combine. And now what are we going to use for the root? Well, we have storage container dot title location, and this will contain an absolute path to the game itself, to where our executable resides. And we can combine that with our content.root directory. Matter of fact, we can simply grab this exactly. Since we know that we have just set content.root directory to content.
So you're getting that path and then basically adding on the word content.
Exactly. So we're dropping into the content folder. And that means, after this operation, content path will contain an absolute path to content. So
now, I know it's going to sound like a ridiculous question, but you don't have to add the slashes or anything.
That's correct. That's where we're leveraging the functionality of combine and letting it worry about what the folder division character is going to be.
Just making sure everybody's aware of that.
So now that we have a path extending all the way to samples, for example, if we look at content path as though we had just navigated here, we need to do one last operation, that is combine content path with samples to get down to this level. So we'll do this by expanding our samples name to an absolute path. So we'll say that samples path is equal to path.combine, and we'll combine content path with samples path. So we're actually taking samples path, combining it with content path, storing that result,
plugging it back into
in samples path. Yeah. Now, to prove that this is indeed working, I'm going to set a few breakpoints and step through these operations. So first we'll set a breakpoint on content path, and then we'll run the game. And immediately we break out here as we're creating the game, and we can see that content path has not even been set yet. But we're about to set it with title location. We can see the path listed here, starting with the C drive, ending with our game's output folder, and the content root directory. So after we run this operation, we will have, I'm adjusting to this keyboard we're using for recording mode. So if we step through that operation, we now have content path being a full path, and then samples path being combined with content path, resulting in samples path pointing all the way down, ending in samples.
Nice.
So we can take the breakpoint out, we can continue execution, and we have our game running. So that takes care of path expansion, getting access to samples path.
But we're still not loading anything up.
That's right. We've got the directory established, but we are not actually utilizing the data contained within. To do that, let's jump down and now turn our attention back to sound engines. Down here in load content, we had the sound engine exact set up. We're going to replace this sound engine exact with an instance of sound engine direct sound. So we'll make a new instance of sound engine direct sound. We'll initialize it, pass the game in, but now we need to address the load sound calls. Whereas with the sound engine exact, we just specified queue names. Here we need to specify full WAV files. So we're going to do this with one final path.combine operation, where we combine samples path with the name of the specific WAV file. For example, crash.wave.
That was easy.
So close off the parenthesis for path.combine, and that should take care of everything else. That's why we went through the effort of establishing the samples path, is now we don't have to worry about finding that path here. Now what I'm going to do is simply copy part of this line where we created path.combine up right before the first quote, just so we can paste that in place for these remaining two calls. Add an additional closing parenthesis to both calls.
And put in your wave.
Put in a .wave to finish off the file name. And that should have us ready to go for loading sounds. At this point, we're ready to build the game and test. So let's compile our game, and let's hit some keys and see if we hear drum sounds. And everything seems to be working fine.
Very cool.
So at this point, we have established direct sound playback for our sound engine.
So technically, we're done.
Yeah, technically we're wrapped up here, but there is one thing to note, and that's the fact that we have just messed with the load sound call here. And if we were to try to go back and forth from XNA to direct sound interchangeably, which was the whole point originally.
Right, well, now we'd be sending in too much information. We'd have an entire path plus .wave, which we didn't have before.
Exactly, and that's not going to be referencing a specific cue. That's going to be referencing nothing as far as exact is concerned. So let's show what the problem is here. Let's change this back to sound engine exact and try running our game. And you'll see that as soon as we try and play a sound, what happens here? Well, we have these cue names, and what do we have? Big long path to something ending in .wave, which are not, in fact, actual cues loaded up here in our sound bank. So let's break out of this and address this here.
So there's two ways you could fix this. One is if you knew you were setting everything back to the exact engine, you could just change all of these load sounds back to the way they were. Or another way would be to fix it on the far end and make it so that when exact receives this data, it knows how to handle it.
Exactly. We could simply resolve, since we can leverage the fact that in the exact project, all of the cues ended up being named based on the incoming samples.
How convenient.
So all we really need to do is simply resolve an original name out of this full path and pass that on to our list, and therefore pass that on to the actual play call. So what we'll do here is back in Sound Engine Exact, we'll go down here to Load Sound. Instead of directly loading a sound name, we'll use another piece of functionality found within the path object, and we'll use that to strip all the path information. Now we're going to drop in here a using to system.io to give us easy access to the path object.
It's funny, because in effect, you're going to make the exact version load information just like the DirectSound version.
Exactly. And in unifying this loading mechanism, we make it much easier to switch back and forth between the two.
Right.
So what we're going to do in here is run path.getFileName without extension. GetFileName itself would pull all the path information out, and without extension will also pull out the .wave part. So let's drop this in around our sound name, and this should get us back to, if we look at one of the sounds we're feeding in, crash.wave, that'll pull off all the path information, and it'll pull off the wave information, leaving us with just the word crash, which is indeed the name of a sound cue.
Cool. Can we test it?
So let's build. We have no build errors, and we're still using Sound Engine Exact. So let's run our game and hit a few sounds. And everything seems to be working just fine.
Awesome. So with that, I guess we have wrapped everything up. We've actually shown how to build a direct sound version of our engine, so that now we can take in that API as well. And we've kind of bolstered the support that we had in Exact as well, so that now we don't have to change back and forth between how we're loading sounds in. We can load them in a single unified manner, and really all we have to change is which engine we're talking to.
Exactly, so it makes it very easy to switch between engines.
All right, so that's going to wrap things up for this video. Thanks a lot.